You go
So
ahead.
I'll
Okay,
begin.
thank you.
My research is on a content-based automatic filter recommendation system for photography and image editing using artificial intelligence. So my name is Yifan, and I'll start with a quick introduction to the issue that I was trying to solve. So, in modern times, the convenience and intuitive nature of phone cameras have given everyone, regardless of their experience in photography, the ability to capture images. The most common issue regarding the phone camera is their image quality. Many people now, they question the final image quality of a phone camera, stating that the images are less sharp or less aesthetically pleasing than what you would see from, say, a professional photographer or the images that you see online. But why? Why is this difference caused? Well, in fact, the camera quality, like the quality between the difference between the quality of the camera on the phone and the camera on the a professional DSLR camera is that's not what causes the difference. So let's first talk about what creates an image. How is an image created? An image is created as light falls on a photosensitive surface. This surface is an image sensor such as a CMOS or a speed sensor. And the most determining factor of the image quality is actually the size of such sensor. It is not like the number of pixels, it's not how how like large aperture you have, it's not about shutter speed, it's about how large the sensor is. And in fact, modern phone producers, they can actually fit 1-inch sensors into their phone, which is the same as some professional cameras, such as the Sony RX100. And that camera sells at $1,000. So that's a really good camera. So this just goes to show that the difference in image quality between the phones and cameras is not just, it's not very significant. And it is definitely not enough to be noticed on small screens. So the question is, what causes the difference then? And in fact, the difference is caused by the color and only the color entirely. Professional photographers often spend large amounts of time processing an image after taking an image in image editing softwares such as Lightroom Classic or Photoshop. This ensures that the color is pleasing, and it will be the first thing that people will notice when they see the image. Mobile phone users do not do the same. They rely on the basic processing by the ISP, the image signal processor, in the smartphone, which does not produce remarkable results regarding the color, making the images look gray and unappealing. So here is just a quick example. On the left side is what an original image on the phone would look like. And on the right side, I just made some simple edits and it looks just completely different. So that just goes to show how color can change everything in an image. So what's our solution? We propose the PhotoGleam mobile application as a solution to the lack of convenient and intuitive image processing tools for mobile phone users. The PhotoGleam application uses artificial intelligence to generate a list of possible filters custom curated for the individual photos itself. So how this works is that the user can take a new photo within the application or upload an existing photo from the image gallery. Once a user decides upon a filter that they like, PhotoGleam will simply apply the filter to the image and make a filtered image available for download. If the user does not like any of the filter recommendations, then the user can request more filters until a desired result is reached. So I want to talk a bit about the design of this. The proposed application generates image filters completely automatically without asking for any additional inputs from the user. All the user needs to do is to press a shutter, then a list of fully edited and processed images will be available to the user, making the proposed application an effective solution when compared to conventional image editing software. Our philosophy is that all the user needs to do and all the user should do is press a button and everything, image editing, processing, will be handled on our part. And before I go in depth into the solutions that we had, I want to talk a bit about the challenges, some challenges I faced during research, designing, and implementing the final product. So first is about the image recognition. At first, we decided to train an image recognition model. However, these were not as effective as we hoped. I believe the issue is because of the small sample size that we use to train our model. Because as everyone knows, the model used is not nearly as important as the quality of our sample. That is the determining factor. In the meantime, we propose the use of Gemini for image recognition since it is a pre-trained model that is not only strong, but also easy to use. But in the future, we will continue to try to train our own model and maybe replace Gemini in our backend function in the future. Another problem that we face is the backend server. So the backend server was originally planned to be deployed and hosted on Render. However, the server's deployment on Render failed. Major delays, and our solution to this was to just do it on AWS instead with an EC2 instance. However, this also had many issues. So there are major delays or timeouts that would disrupt user experience. And to resolve this issue, we could attempt to optimize the server's performance by implementing load balancing and caching mechanisms. Scalability is also another major issue. As the server gains popularity and user demands increase, it is crucial that the server's architecture is scalable. A last issue that we experienced was in the Flutter frontend UI. Existing issues on the front end include lag in UI responses and heavy processing load, and the complexity of providing real-time filter previews. Optimizations such as efficient state management and leveraging asynchronous processing can be considered to alleviate these issues. Okay, now let's finally get into our solution, PhotoGleam. So there are three major components to PhotoGleam: the Flutter-based front-end UI, the Flask back-end server, and the AI image processing engine. Here is the flowchart of PhotoGleam, the mobile app that we developed. So the application flow begins when the user captures or uploads an image from the mobile phone, after which the image is sent to the Flask server immediately. In the Flask server, an AI image processing engine is utilized to generate and apply the custom filter. More specifically, an API call to Google's Gemini AI is performed, in which Gemini analyzes the image, considers various factors such as lighting, color, and composition, and then Gemini returns a list of image adjustments back to the Flask server. In the server, the suggestions are applied to the image utilizing Pillow, utilizing Pillow, the Python imaging library. Finally, the edited images are returned to the application where a user can preview them by scrolling left or right and download the desired edited image to their drive's local storage. If the user is still unsatisfied after all these steps, then the image can be uploaded again and a new list of filters will be generated again with the press of a button. Okay, let's move on. So first, I want to introduce or talk a bit more about the AI processing engine. So the AI processing engine is a corporate component of PhotoGleam that generates and applies custom filters to images uploaded by users. This component leverages Google's Gemini AI to analyze the images for suggestions and utilizes Pillow Python imaging library to apply suggested enhancements. This makes it possible to deliver unique and tailored filters to the user. Here is some sample code that I did. The provided code illustrates the implementation of the processing engine, which contains two parts: the Gemini AI filter recommendation and generation, and Pillow PIL to apply the suggested filters. So the first code snippet illustrates the API call to Gemini for filter recommendation, which is the first major part of the processing engine. In the code sample, the request Gemini function takes in two parameters, the image and the AI model, and then sends an API request to Gemini. In the API request, a predetermined prompt is included alongside the image asking for filter recommendations in terms of brightness, contrast, color, and sharpness. The return format is specified to be in JSON. The second code snippet illustrates a breakdown and application of the response from Gemini and Pillow. After the JSON data is received back from Gemini, the breakdown filter function is called, taking in return data as a parameter. This function breaks down the response into filters and suggestions. Then the apply filter function takes in the filters broken down in the breakdown filter function in the original image as parameters and applies the filters onto the original image using pillow. Now, next, let's talk about the Flask backend server. The Flask backend server manages the interactions between the Flutter front-end UI and the AI image processing engine. It handles things such as image uploads, communicates with the AI model to request filter suggestions, utilizes Pillow to apply these filter suggestions to the original image, and returns the filtered images back to the user. The Flask server ensures the smooth and secure processing of these images. So here are two sample code that were in the backend server. In the first code snippet, the get filter route handles the HTTP request for the image uploads. Upon receiving the image, the server saves it temporarily and uploads in the uploads directory. Then the config Gemini and request Gemini functions call the image processing engine to initialize Gemini, generate custom filter data, and return them. The returned filters are sent back to the users in JSON format. In the second code snippet, the get image route handles the HTTP request for the filter applications. After receiving the image and filter suggestions, the server saves the image temporarily and calls the breakdown filter function and apply filter function in the image processing engine. These functions apply the filter to the image utilizing Pillow, and the filtered images are finally sent back to the user. Lastly, we have very important part, the front-end UI. This is an essential component that allows users to take and upload images, display custom-generated filters for these images, and download these filtered images to their local devices. This component interacts with the backend server to send the original image, receive filter suggestions, and receive filtered images to display the final result in the mobile application to the user. We chose Flutter because of its multi-platform compatibility, so we only need to develop once, and it can be deployed on Android, iOS, and all these different platforms. So here is an overview of the UI design. We have a home, we have homepage, upload page, gallery page, and the profile page. In the homepage, there is a tips and tutorials, and there are quick keys to access all the other functions. But the main part is in the camera. So when you press the camera, you can take a picture, and after you take it automatically, images will be uploaded to our server, and you'll receive suggestions. And the suggestions are here in the middle screen. So you'll be able to swipe left and right to see the different suggestions, and then save the image to the gallery, which you can view later. And then this is a code sample. So in this code sample is within the filter screen page and demonstrates Flutter UI's functionality for applying filters to images within the PhotoGleam application. When the page is initialized, the apply filter function is triggered, sending the image and selected filters to the backend server via an HTTP post request. Okay, next, I want to talk about the experiment. We did two experiments, the user satisfaction experiment and the user engagement experiment. So first is the user satisfaction experiment. The goal of this experiment is to test the accuracy and effectiveness of the AI-generated filters in enhancing image quality and user satisfaction when compared to, say, standard filter options. To test the filter accuracy, we will conduct a blind comparison involving 15 participants. Each participant will be presented with two sets of images, one set with standard filters and another set with AI-generated filters from PhotoGleam. The images will be displayed in a randomized order without any indication of which filter was used. Participants will be asked to rate each image out of 10 based on its overall visual appeal, color balance, and perceived quality. Here are our experiment results. The AI filters scored an average of 8.1 to 8.4, significantly outperforming the standard filters, which scored between 6.5 and 6.8. This result suggests that the AI-driven approach effectively enhances image quality in ways that are both noticeable and appreciated by users. Our next experiment is the user engagement experiment. This experiment aims to evaluate whether the introduction of AI-generated filters in PhotoGleam leads to increased user engagement, measured by the time spent on the app and number of edited images per use. To measure the user engagement, we will track the app user statistics of 15 participants over a 2-week period. Participants will use PhotoGleam app with both standard and AI-generated filters available. The experiment will monitor 2 key metrics: the average time each participant spends editing images per session and total number of images edited. Here are our results. So participants spent an average of 8.5 minutes per session editing images with AI filters, compared to the just 5.2 minutes with standard filters. Additionally, the number of images edited nearly doubled, from the 18 images using standard filters to 32 images with AI-generated filters. These results suggest that the introduction of AI-generated filters not only enhances the quality of images, but also significantly boosts user engagement. So here are some related works. The study in 2022 focuses on enhancing image sharpness and using dilated filters in digital photography. The authors propose an enhancement of traditional sharpening algorithms, like the high-pass filter or unsharp masking, by incorporating dilated filters. These modified algorithms are shown to achieve better results both visually and statistically compared to classical methods. However, this approach is limited by its reliance on traditional filtering techniques, which may not account for the complex image characteristics. In contrast, PhotoGleam leverages AI to generate custom filters tailored to each image, providing more flexible and high-quality enhancements. Another study introduced deep local parametric filters, deep LPF, for automatic image enhancement. Their approach used deep neural networks to apply spatially localized filters, offering more refined adjustments compared to global enhancement and techniques. While this method excels in providing interpretable and intuitive enhancements, it still requires significant computational resources and might be less accessible on mobile platforms. The PhotoGleam application improves on this by integrating AI-driven custom filters directly into a user-friendly mobile application, making advanced image processing more accessible to the average user. Another related work is MIEGAN, a generative adversarial network-based method for enhancing mobile photography images. It uses a multi-module cascade network to improve image quality, particularly in low light conditions. The method successfully balances global and local enhancements, but its reliance still on high computational power can limit its use on resource-constrained mobile devices. In contrast, PhotoGleam offers a much more convenient and efficient solution by using AI to generate filters that require minimal user input, allowing for real-time processing on mobile devices without compromising the image quality. Finally, let's get into the conclusions. So there are many limitations on our work. One major limitation is the dependency on the backend server for filter generation, which may cause delays in processing, especially under high user traffic. To improve this, implementing a more robust and scalable server architecture could mitigate latency issues. Another limitation is the heavy reliance on Gemini for filter recommendations and suggestions. In the event that Gemini is not available, PhotoGleam will not be operational, as no filter suggestions will be returned. The entire function of PhotoGleam depends on Gemini being functional. Additionally, Gemini occasionally has issues retaining data that in the request JSON format. This issue can be addressed by training a new image recognition model that can recommend custom filters based on the content of the image, as talked at the beginning of this presentation. Finally, the user interface could benefit from further refinement to enhance the overall user experience, particularly in making the camera more functional by adding more zoom, focus, and exposure options. In conclusion, PhotoGleam presents a novel approach to mobile photography by leveraging AI to generate custom filters that enhance image quality and increase user engagement. While there are areas for improvement, the app's current functions, intuitiveness, and effectiveness position it as a valuable tool for both amateur and professional photographers. Thank you for your time and thank you for listening.